Hello students, let us start our discussion on certain properties of inner product. So as we have learned about dual spaces and inner product or scalar product in our last class, what we saw are that there are certain properties that we can associate with inner product. They are kind of intuitive and they are not that difficult to perceive, but still if we write them down once and for all, that all these properties that we note here and there in that first operation in this linear vector space that we have learned, that will be great. So let us see what are those properties. For example, in the last class we noted that in case of inner products, in general, because the vectors could be complex, in general bracket phi psi is not equal to bracket psi phi. That means that when you interchange them, it does not happen like the normal vector space that a dot b is equal to b dot a, but if we note carefully, then you can see that there is a complex conjugation that happens right there. So that means that bracket phi psi is equal to bracket psi phi star. It is not very difficult to prove that why this happens. So if we just check quickly, then let me have one vector in the linear vector space, n-dimensional linear vector space in general, which looks like alpha 1, alpha 2, alpha 3, dot 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 alpha n. These are all components of this vector phi. And there is another vector from the same linear vector space which is psi, and their components are beta 1, beta 2, beta 3, dot 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 beta n. Just remember that both of them are general quantities, and in general these elements could be complex. So if that is the case, then how will we calculate bracket phi psi? So if we want to calculate bracket phi psi, then that means psi, which is in the ket form, that will still remain in the column vector format. But for phi, we have to go to the row format or to the dual space. So as soon as we convert or look at the dual space counterpart of phi, we have to convert, as we learned in the last class, we have to convert this into row. Not only that, we have to take all these elements complex conjugate counterparts. That means instead of having alpha 1, alpha 2, alpha 3, dot 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 alpha n in the row vector, what I will have is alpha 1 star, alpha 2 star, alpha 3 star, and so on. And when you do the matrix multiplication, what will you have? For this one, you will have alpha 1 star beta 1 plus alpha 2 star beta 2 plus alpha 3 star beta 3 and so on, right? But in the same way, if you consider that what is going to be my bracket psi comma phi, psi phi, bracket psi phi, right? Then in that case, your phi will remain as the column vector, and your psi is going to become the row vector or the counterpart from the dual space. That means your betas are now going to be converted into their complex conjugate counterparts, and you have to multiply them in front of writing them in row form in front of your column vector, which is your phi. So in that case, what will you get? In that case, you will get beta 1 star alpha 1 plus beta 2 star alpha 2 plus beta 3 star alpha 3 and so on. So immediately you understand that there is just one set of complex conjugation involved in these two quantities. So we can in general write that bracket phi psi is equal to bracket psi phi star, right? So you have to consider this star. Without it, the statement would be wrong in general if you consider for complex quantities. If both of these vectors are real quantities, all of the elements are real, then this star does not matter, and that is what happened in our R3 in our vector space, that is we consider I hat, j hat, k hat Euclidean vector space, and for that reason we had a dot b is equal to b dot a, which is not in general true for complex vectors. So this is what we noted here, that bracket phi psi is equal to bracket psi phi star. This is one of the such properties of inner product that we have already noted, and this is very intuitive, but it is good to write them down once for a rule, right? This is kind of a rule that we will remember, right? And this is very intuitive. This is why it happens is very, very easily understandable, but it's still better to write them in form of a statement or a rule so that you can use it very frequently later on in our calculation. So this is one of them. So similarly, if you look for the length, we defined the length in the last class, right? And we noted that what will be, if I want to calculate the length of a certain vector, say psi, right? And let us consider that its components are alpha 1, alpha 2, alpha 3 and so on. And I want to calculate the length. So following the same notion of length in our normal vector space, we did something like this, bracket psi psi, right? So this quantity bracket psi psi basically represents the length square, and we saw that it is going to be that alpha 1 star into alpha 1, alpha 2 star into alpha 2. That means you take mods of them, squared them, sum them of all, and that is going to give you the length square. So as we discussed in the last class, we should not call it a length now because it's not basically physically represent any length. So what will you call them? We need a new nomenclature. So for that, we define something called the norm of a vector, and this is nothing but the same quantity that we have just defined. So what is norm of a vector? Norm of a vector is generally defined by this special kind of braces, two lines on both sides of the vector, and here you note that there is no bracket sign here, right? There is no angular brackets here. It's just the quantity that you write inside the angular brackets. So just the name of the vector or something like that, because it's just a value. We are talking about the value, right? Length or something like that. We call it a norm. So double lines, double braces on both sides, straight. This is the notation for norm. And norm basically means that you calculate the inner product of psi with itself, and whatever the quantity you are getting to the power half will give you the value. So it's like you are calculating the modulus square and you are taking the root, something like that. Similar, right? Similar notion. So here it's important to note that as these are all complex conjugates of these numbers here, so once you multiply them all, what you are supposed to get is a real quantity, right? You're not going to get any complex numbers here. Even if in general case where all your quantities, all your components are complex, once you do this calculation, you are going to have something like a length or a physical value which is a real value. That is first to note. And second is this real value should be greater than or equal to 0. Basically to ensure that only, in the last class we have seen that to ensure this only, we have taken this particular approach where we converted all these row vectors into complex conjugates. So what we note here, we note that first the norm is a quantity which is real and which is positive, which is only 0 if and only if it's a null vector. That means all the components separately, alpha 1, alpha 2, alpha 3, every component of this vector, if everyone is 0, then only you can have norm is 0. So this is another property, right? This is another thing that we note, and this is also very intuitive, but it is also something very, very important that we have defined norm, that is the notion of length in general for linear vector spaces. We noted that it's a real positive quantity and it could be 0 if and only if it's a null vector. So this is another point to note. Just like that, there are several such properties which are very easily understandable and still very easily, you can prove them very easily, but they are very handy as well. So let me just go through them one by one. So the first one is just the one that we have just defined. That means the value, the norm of a quantity, norm of a vector is a real positive quantity and it is 0 if and only if alpha is a null vector. That is the first point that we note. Second one is that when you calculate the inner product of any two vectors, right? You calculate inner product of any two vectors. In general, this could be a complex quantity. There is no necessity that this is going to be a real, but once you do the modulus square of that, that means suppose this is z, certain complex quantity, and you are doing mod square of that, that is going to be a real quantity, right? So when you, for a single vector, bracket alpha comma alpha, that means the value of the vector, the norm of the vector, the length of the vector, that is real. For two different vectors, you have to take modulus square to get a real quantity. Okay, that is the second property that we see. The third property is the one that we have just discussed, that if you have bracket alpha beta, that should be equal to bracket beta alpha star. So a complex conjugation is involved in the inner products if you swap. If you take A and B's inner product and if you take B and A's inner product, there is a complex conjugation involved in general. not applicable for real values, obviously. This is an associative property, and this is also very straightforward. This is also something that we have discussed, that could be derived from what we discussed in the last class. What is written here? Suppose you have alpha, and this is the other way around. This is a Bra vector. So the Bra vector, that means which you are taking from the dual space, you are multiplying that, taking a dot product or inner product of that from a certain vector, which is weighted addition of two vectors from the original vector space, beta and gamma, and I am calling it weighted average because you are taking p times certain scalar time p and q, certain scalars time beta and gamma, and you are multiplying them. So what you will get as a result, when you will do this calculation, you will take this quantity, the scalar out, and then you will do the inner product of alpha and beta. Same here, take the scalar out and do the inner product of alpha and gamma. So this is the associative property, right? This is also something that comes in very handy in doing the calculations, and we will see it very soon in this class only. After these four are very intuitive. These two properties also are very important, though not very intuitive, but also very easily you can relate it with what you have in the real vector space. So let me discuss them one by one. The first one, that is on norms, right? So it tells you that if you have two vectors alpha and beta, and you alpha plus beta's norm, alpha plus beta is one vector, alpha is one vector, beta is another vector, you do alpha plus beta and take the value of that vector, norm of that vector, that is always going to be lesser or equal to alpha's norm plus beta norm, right? This you can easily relate to normal vector spaces. So suppose you have two vectors x and y. This is basically triangle inequality that you see in vectors, right? So you have alpha x and y, right? So the third vector, the third component, the triangle, the third one is only going to be equal to the values if they are all collinear. Otherwise, obviously, these two are going to be more the higher values compared to what you have in the third arm. So this is basically just the values of the triangles, right? So if the third arm is always going to be shorter compared to what you have in the other two arms, and that is very obvious. In terms of length, if you only consider in terms of length, that is what we have. This equality, the equality sign only holds if these two vectors x and y both are collinear. If they all lie in the collinear, the triangle flattens and you have z is equal to x and y in this particular diagram, and alpha plus beta is equal to alpha plus beta in this particular notation. But this is not only in our ordinary two-dimensional space where I have drawn this triangle, but it is true for any linear vector spaces, and this is a general statement, right? The second one is called Cauchy Schwarz Inequality. So Cauchy Schwarz Inequality is also a very, very powerful statement, right? And we will talk about this particular statement in further detail in today's class, and also we will learn that how to basically manipulate the simple intuitive properties that we have written, the four properties that we have written on inner product, how we can use them to manipulate and prove certain interesting things, right? So what is Cauchy Schwarz inequality? It tells you that suppose you have a vector alpha and a beta, two vectors you have. So in these two vectors, if you take the inner product and you do modulus square, then this value, this is a value, this is some real value that you will get, right? This real value will always be lesser or equal to inner product of alpha with alpha and inner product of beta with beta. Both are real. So if you multiply them separately, then this is going to be always lesser or equal to that. So what we are actually trying to say here, let us again go back to the same examples, the vector examples that we are comfortable with. So basically what it is telling is something like this. Suppose you have two vectors, right, a and b, and if I take dot product of these two vectors, this is the dot product, right? This is the dot product, inner product. So the same related operation in our vector space, normal Euclidean vector space, will be taking a dot product a dot b. So just consider that I have a and b, two vectors, and the angle between them is theta. I am taking dot product. What is the value a dot b? A dot b is a mod and b mod and cos theta, right? So ab cos theta, that is what we write. So basically what we have here is something like this. That suppose I have two vectors, say A and B, and I am taking the dot product of these two. So what I get? A mod, A vectors mod, B vectors mod, and cos theta, right? So AB cos theta is A mod B mod cos theta. So if you remember what we have written in the Cauchy Schwarz inequality, that basically talks about square of this quantity. So if it is a scalar number, right? A dot B is a scalar number. So similarly, just consider this is a scalar number, and I am taking a square of this. A dot B, whatever the value that I get, I am taking a square of that. So if I am taking a square of that, then what do I have here? So I get A mod square and B mod square and cos square theta, right? So as soon as I write this, what I note here is that this quantity cos square theta can only have values which are lesser than 1, right? Cos square theta is less than equal to 1. So that immediately tells you that this, if I compare these two and I remove cos square theta from the picture, this equality will turn into an inequality, and it will tell me that what I have on the left hand side, this quantity is always going to be lesser or equal to A mod square, B mod square, right? So this is the counterpart. This is the counterpart of Cauchy Schwarz inequality. If I consider this statement in our usual vector space. This is just basically telling you that cos square theta has a value between 0 and 1, and from there you can directly understand that what I mean by this inequality. But as I told you, this particular statement that we just have given is much more powerful than what we have in this vector small vector calculation that we did, right? Because if you just carefully see that the most interesting statement of quantum mechanics that we have learned till now is the Heisenberg's uncertainty principle, right? And it involves an inequality sign. So we cannot ignore the simple results that involves inequalities in quantum mechanical calculation, in linear vector space calculation, because they might have immense amount of physical interpretation. So the Cauchy Schwarz inequality is also something like that. This is the statement which we will use very extensively to establish very powerful results. Basically, uncertainty principle. So at the mathematical level, uncertainty principle follows the Cauchy Schwarz inequality. We will prove that, and that's why it's very important to understand and to learn how to prove this statement. And this is also a nice training exercise of how you can use the properties that we have just written down on scalar products to prove certain very interesting results. So let us try and prove Cauchy Schwarz inequality. So to prove this inequality, we will again use the first 4 lines, the properties that we have just written, and which are very intuitive, and you can easily prove these properties also, right? So that how the norm is a real number and it's only 0 if it is a null vector, and how you can say that the inner product of alpha and beta is just the complex conjugate of inner product of beta and alpha, and the associative property which we have written here, right? So these 3 properties basically, these 4 properties basically we will use to prove our Cauchy Schwarz inequality, which is this last line, right? So let us try to prove that. So to prove that, what we start with is a vector, right? So let us consider that I have a vector, and this vector looks like this gamma, and there are several different ways. I must say that there are several different ways to prove this Cauchy Schwarz inequality. I am just showing you one. You can also look for other proofs that are available in different books, and you can use that to establish the same thing. The most important thing is that to learn this manipulation. So we start by defining a certain vector gamma, which belongs to a linear vector space where both alpha and beta are also there. So and this is a linear combination of alpha and beta. So how does this new vector look like? It looks like beta minus alpha beta bracket, alpha bracket and alpha ket. So you can see alpha beta bracket is some number, complex or real. Alpha bracket is also a number which is a real number, and this total thing, that means this entire thing is basically giving you a fraction, right? Certain scalar quantity. So this is basically a scalar quantity. Beta is a vector from the linear vector space, alpha is a vector of linear vector space. So what you are doing is one vector minus certain scalar times another vector. So this gives you another new vector in the same vector space, which I am calling as gamma. Okay, clear? So this is the first vector that I choose to prove the inequality that I am going to prove. So next step is I will calculate a quantity like this, gamma and gamma inner product of gamma and gamma. So how will I calculate that? That means I have to take gamma and I have to take the Bra vector of gamma and multiply it with this. So for that we will use this fourth property, right? The associative property. I will use that and we will write accordingly. So we will write gamma beta, right? Inner product. And then if there is a scalar, as this is a scalar, what we decided that we will take the scalar out. So I will take the scalar out and multiply inner product gamma with alpha, right? So this is what I get. So this is what I get. Now I will separately calculate these two quantities, this one and this one, and we'll see that what is the final result, right? This also teaches us about the manipulations in this particular notation that we have learned. So I'll go slowly and you can follow simply what we are trying to see. So I'm going to calculate bracket of gamma beta. What is bracket of gamma and beta? So as we have seen from this property, the third property, that gamma and beta bracket would be beta and gamma's bracket star complex conjugate. So I can calculate basically this quantity beta gamma bracket, and if I take a complex conjugate of it later on, then I will find what this quantity is. So I am taking that route, right? So I will take beta gamma and later on I will take a star of it and I will get this quantity. Okay. So what is beta gamma bracket? So beta gamma bracket is where I will replace this gamma ket with its definition that I have defined here. Okay. So next step, I will write down the value of gamma that we have, right? So this value, that means I am writing something like this, beta minus alpha beta alpha alpha alpha. Okay. So now I will take this beta inside, right? So this is beta. I am taking the beta inside. So I am taking the beta inside means what I have, the first quantity, there is no scalars involved. So I will have beta, right? Minus second quantity, there is a scalar. I will take again the scalar out and beta will go inside. So I will have alpha beta divided by alpha alpha beta alpha. Okay. Fine. So now what do we note? Here we have alpha beta. Here we have beta alpha, right? So what is beta alpha? Beta alpha is basically third property, star of alpha beta, right? So I will do the same thing. So what I will write, instead of this quantity, I will write alpha beta star. Okay. So alpha beta star, alpha beta is what? A scalar. Alpha beta star is also the complex conjugate of that. So if you multiply them, what will you get? Alpha beta mod square, right? So this is say z, this is z star, you multiply them. This is basically modulus square. So I will do that in the next line. So in the next line what I have is this beta minus, here I have alpha beta mod square, right? This is alpha beta, this is alpha beta star, alpha beta modulus square by alpha alpha. Okay, fine. note two things, that all of these quantities are real quantities, right? All of these quantities are real quantities. Our properties tell us that if any vector multiplies with itself inner product, I get a real positive number, and it is 0 only if it's a null vector, otherwise it's real or positive. Similarly, if one vector multiplies with another vector inner product and you take its modulus square, as you are taking the modulus, obviously you are turning it into a real number. So this is a real number, this is a real number, this is a real number. All of them are real, right? So if all of them are real, then it simply means that beta gamma, inner product of beta and gamma, which should be equal to inner product of gamma and beta star, because it is a real quantity, because all are real, so this star does not matter, right? So I can write this as gamma beta. Taking a complex conjugate of real number does not matter. So beta gamma, what I conclude from here, that beta gamma inner product is gamma beta inner product, which is equal to this quantity that I have here, right? This quantity. Okay. So the first part, this part of whatever I was trying to figure out is here, right? So what we are learning here, we are learning these manipulations, and we are also gradually approaching quantities which are there in our Cauchy Schwarz inequality. So if you look into the expression of the Cauchy Schwarz inequality that I want to prove, it has alpha beta inner product modulus square, it has alpha alpha inner product, it has beta beta inner product, and I have all those quantities here now, right? So I am on the right track. Okay. So let me just remove what we calculated and only keep what we have to use later on. So what I have proved up to this point is that our quantity, the first term, this first term, right, this term is equal to this. So I am writing here gamma beta inner product is this. So this is what I will need, right? Okay. Now let us go for the second term. So for the second term, the second quantity that I have in the second term of this gamma times gamma is this quantity, right? This quantity. I have to calculate this quantity, and I will take again the same approach. Instead of calculating gamma times gamma inner product alpha, I will calculate alpha inner product gamma. So I will calculate here alpha inner product gamma, and I will do the same thing later on. I will take a complex conjugate and check. Okay. So I am doing alpha inner product gamma instead of gamma inner product alpha. I will do complex conjugation later on. So again I will replace, right? Again I will replace gamma from here. I will take the value and replace here, right? So I will have, now I will write directly. So alpha times, here I have beta, right, minus alpha beta alpha alpha, and here you have an alpha ket, here you have a alpha in the bracket, so alpha alpha. Immediately what you see, this quantity is 0, because this alpha alpha will cancel with this one, right? Both are numbers, they will cancel easily. Alpha times beta, another scalar, alpha times beta, another scalar, inner product, so it cancels, so it becomes 0, right? No need to do any complex conjugation, anything. You immediately note that this quantity which I had here, which is the complex conjugate of this quantity, is 0. So this entire term drops down to 0, right? So what I have here now, I have that gamma inner product gamma in this, for this particular gamma that I have considered, gamma inner product gamma is gamma inner product beta, which is something like this that I have already written here. So let me just clear the slate once and write what I have here now. So what I have here now is something like this. What I have here is that gamma times beta inner product is basically equal to gamma times gamma inner product, and that is this. That is this quantity. Now I will use one more property that I have here, and you can easily see by now that which property I am talking about. This is that gamma times gamma. So gamma times gamma, in our property list, it is written that any vector when multiplied with itself, it will be a real positive number, right? It's going to be a real and positive number. So this is also a vector of the linear vector space, right? So this is also multiplied with itself. So this quantity, what I have here, I have already noted that it's a real value, but what I note here now is that it's a real positive value, right? Because it is gamma times gamma. So gamma inner product gamma is going to be a value which is greater than equal to 0. So as soon as you write this, from that simply you can quickly see that the result follows. So the result that we were trying to prove, that alpha beta inner product square must be less or equal to alpha inner product alpha and beta inner product beta. So this is our final result, right? This is the final result. This is the Cauchy Schwarz inequality. It's a very powerful statement. It's a very powerful concept, and it mathematically establishes several physical quantities which can be related through this inequality. And you will soon see, as I already told you, you will soon see that one of these results actually involves the generalized Heisenberg principle and also the Heisenberg principle, that uncertainty principle that we are familiar with. The usual form of the uncertainty principle is basically a corollary of this general inequality that we have, right? So I have written down all the 6 properties here. I have proved which looked most complicated, that is the Cauchy Schwarz inequality. Try the triangular inequality, and I'm sure you will be able to do it. Try in the same way, right? Consider that alpha and beta are 2 vectors, KED vectors, right? Alpha and beta are 2 KED vectors. And you go back to the definition of the norm. Definition of the norm, how it defines, you multiply them and you try to prove from there that this inequality also holds good, right? So I'm sure that you will be, maybe you will struggle a little bit, but once you find the way, it's not that difficult. It's very easy and it will very easily related to the particular equation that we have written here, right? So start from the definition of the norms and try to prove the triangular inequality. So great. So now we are talking in a mathematical language and we are trying to relate more general principles in terms of linear vector spaces. We'll continue on orthonormalization, and because we have already defined the term norm, and now it's time to go towards orthonormality and orthonormalization rules and ways of doing defining orthonormal basis and those things in the later classes. So till then, just try out these problems and try to grasp that how you are doing this, because this is a new kind of mathematics that you are learning, just like when we learned matrix algebra, just like when you learned vector algebra. It's something like that. You are learning a new kind of mathematics, but it's based on something that you already know very well, matrices, right? So that you know very well. So I'm sure that you will be able to handle the notation. Only the notation part is new, right? So don't get afraid of it. Try out, and I'm sure you will be able to learn the basic manipulations pretty fast, right? Let us stop here for today. We'll continue on orthonormalization and more things in the coming classes. Thank you.